Hey, good evening, everyone. Hope you have a wonderful weekend and Eastern. So let's start with our today's content. If you still remember, last time we talked about different kinds of reverse engineering or say binary analysis tools. And we mentioned like static analysis, dynamic analysis. And also we talk about a specific binary stoplet there. So today we're going to continue to talk about those interesting and useful binary analysis tools. And we're going to use this example. So right now, you could either just like watch what I will do for using like 4 approaches to solve this challenge, or you can spend some time to download this file and try to play with it. So if you have a Linux machine right now, it's great that you can run this binary. If not, you can also just try to analyze this statically. Okay, so here's the slides. Sorry, not the slides, but here's the link of the binary. If you click it, I mean, you can't really click it, but like if you copy paste the, oh, sorry. Let me go that back. Let me copy paste the link to the chat so that you will be able to just click it. All right, and let me share screen again. Cool. Okay, so now you should be able to just like click and download. And I will first give you a couple of minutes, try to figure it out. What is the key or say the flag hidden in this binary? And if you have the answers, then just show me, just copy paste the answer in the chat. Cool. So I saw some of you already get the right answer. Matthew and Jose have the correct answer. And also, Matthew and Jose, since you got the answer, can you briefly talk about how did you get that in chat? Cool. So I saw Matthew, Jose, and Benjamin all says that they just open the file and then look at the text. And a Hunter uses the tool called strings. That's nice. Okay, cool. So this is a simple challenge. However, we can solve this challenge in many different ways using simple or more comprehensive tools. And I'm going to talk about 4 different ways that you could, use to solve this problem. So the first is going to be strings. And give me a second, guys. I'm going to share my virtual machine with you. Okay, so now you should be able to see my terminal. I'm zooming it more, and now it's bigger. Okay, so here is the binary example, the out. And if you are trying to run it, then you will see this. It will ask you, for this book, Harry Potter's first book, how many pages in this book? Let's just take a guess, like 1, 2, 3, okay? And then it tells you that you're wrong. You have to keep going until you get the right pages. And once you get the right pages, it will output the flag. And now let's suppose that we don't know about this logic. Like you only run the example and then you type some numbers and it tells you that you're wrong, keep going, okay? Then the first way, as Hunter mentioned, is that you can just use strings to kind of output the readable strings along with this binary. Okay, so we just do strings.out. And there are many, many of them, right? And we can use the less command to show it, not all of them in one time, so that you can just do that. You can scroll up and down in order to find the key. All right, so here it says that you're correct. Your key is this. I should have changed this to our course, but whatever, that doesn't matter. So this is the right key. So basically this is the right key, right? So this is one way that you can find the correct key. And also, as Benjamin, Jose, and Matthew said, you could just open this using text editor and look at the strings and to see if there is any interesting strings. All right, so this is like method number 1. Use strings or open that file, use text editor to open the file and to explore around interesting strings that might be useful to you. Cool. And then next, let's try the second approach. I am going to use Ghidra. So tell me, how many of you have heard about Ghidra before? No? Okay. That's totally not a problem. You will know Ghidra very soon. So let's try Ghidra. Ghidra basically Yes, I mentioned Ghidra for one time, but like Ghidra is a binary analysis or a reverse engineering tool helping you to understand the program behavior, or say the program semantics. And now I'm going to open Ghidra, and then we can work on, like, use Ghidra to work on this challenge together. And if you have Ghidra installed already, then you can do this with me together. Otherwise, you can just watch me. Okay, so I'm going to open Ghidra. Okay. Okay, now we open the Ghidra, and let's just start with a clean project. So usually you do file and you set new project. And you could either share or not share, but usually I just do not share because, you know, you just want to do that by yourself. You're not gonna share this project with other people. So you can just do not share project, click next, and then you can specify the name. And I'm gonna change that to our current folder, which is course, not there yet. All right, and then I'm gonna just put this over here. Class 4. So actually, I'm gonna just put that in that folder and call the project's name as class 4. Okay, and then finish. Now we create a new project. And then the next, we're gonna import the binary to be analyzed into this project. So can do file again. And import file. And then we import the binary. Now we see that the binary is included in the project. And then we just, okay, click OK. It gives us some overall information. And then we just double click. And it will open a new window containing this binary. And you see those, like, in the background, behind this window is actually the program's content. Okay. And now it asks you, like, would you like to analyze it right now, since example.out has not been analyzed before? And then we're going to say yes. I'm going to click this for decompiler because we like to use decompiler features for Ghidra. And we analyze it. And now we find the functions that we're interested in. And probably I'll just start with main because, you know, that is the start, usually like the start of the source code when we write source code. Cool. And now you will get a decompiled source code on the right-hand side panel. And when I say decompiled, it's the opposite of compiled. So this means that you're given a binary, given an executable file, and the Ghidra will help you to infer back the source code according to the binary file. So you see that this is the decompiled code, and it's not going to be exactly the same as the source code. For example, you see like those variable names, they're no longer exist, they just they lost, but they use another name to kind of like another string to name the variables, but that's okay. And we find that this is the program, and it has this interesting statement. It says that it's going to output a string, right? With this string, you're correct, your key is this CSE545, good job. So you got that, okay, this is the key. All right, so this is another way for you to get the correct string. So instead of using the strings, instead of using this like strings command, you can also just use the compiler to open the program and then understand what the program does and find interesting content or understand the semantics so that you know what should be what the key should be. All right, so this is approach number 2. And now let's try approach number 3. And before that, I have a question. So I noticed that Jack Summers mentioned that the number of pages is 223. So Jack, could you talk about how did you get this number? You can either chat, you can either speak or type in chat. Okay, so Jack says Google pages in Harry Potter and the philosophy. Okay, that's a very interesting thing. Yes, I mean in theory you can also do that because it asks you this value, right? And if this is something that's kind of common sense, then you can Google it. And then my question here is there a way for you to look at this binary, or say to not really, when I say look at, it doesn't limit. It doesn't mean that you just limit yourself to static. Like, is there a way for you to figure out this number, which is 223, from this binary? All right.
It
Yeah.
looks like I'm not sure which one, but it looks like it's stored in local 10 or local BC. I think line 12 is it. So if you could you would take
Mm-hmm.
that and convert
Mm-hmm.
it to
Yeah. Mm-hmm.
decimal,
Yeah.
I think.
The direction is correct, although the variable is a little bit different. But yeah, you're definitely on the right track, Jack. So what we could do is that, as Jack said, we can try to understand this and then see that, because ultimately this is something that we want. We want the program to output the right key to us, right? So then we want the program to execute this statement. And for that, we have to make line 18, this statement, to be true, correct? And then let's take a look at these two arguments, local 20 and local 8C. And for local 8C, we found that this comes from the upper statement, which is scanf. So it has a scanf, and then we know that for C, scanf, usually there are two, or there are like a multiple arguments, but usually the first argument would be the format string. And let's see what it takes. So we can click this, double click, and we found the corresponding format string, that is %D. Okay, so now we know that actually scanf tried to read %D, so which is the integer, and it will save the value of the integer into variable local 8C, right? And then it will compare local 20 against the local 8C. And this comparing statement happens at this particular address. Oh, not this one, that one, compare, right? Because now if I click here, it will go to this statement. So there's a comp. And then if this compare is not equal to 0, meaning that they're different, then they will jump to somewhere. Otherwise, they will do put, right? Okay, so now we know that this address is a critical address. And then we want to go to this address. Then now let's use a dynamic way to analyze this program. And I am going to use GDB to do that. Okay, so what I'm going to do is I'm going to use GDB and then try to run this program and then set a breakpoint at this particular instruction at this location, stop over there, and then check the values of EDX and EAX. All right, and now let's try to do that together. So I'm going to come back to the terminal, and I'm going to do GDB example.out. Okay. And the next that I'm going to do is I'm going to copy paste this address because I know that this is the instruction address that I want to jump to and I want to stop at. And that is hex 100914. Okay, let's do that. 100914. Okay. And now let's start to run the program. I use run, or I just type R for short. Okay. Well, there's a problem now. We set a breakpoint, right? We just do that, and then we can show the breakpoint again. This is the address. However, if you look at disassembly, which shows the current disassembly, like the current instruction, it goes to somewhere else. And then what it is, we don't know. But now we know what we know about a program. If I have another window, I try to open it, right? And then I run that. It will stop back here. It will first ask you those values, right? So we know that, well, maybe this is the place that it starts to ask you this value. So now let's just try to continue, see if there's anything showing over there. Nope. Okay, so it says that, and especially says that it cannot access memory at address this particular location. This is weird because we know that there's supposed to be an instruction over there, but why it says that there's no memory at this address? And the reason for that is because for GDB, when it debugs a program, and especially if the program is the so-called position independent executables, let me see if we can get that here. File example out. I don't know if that shows that. Okay, it doesn't show that, but that is fine. So example out is position, what is called positional independent executables. It means that it goes with the offset. So, but for GDB, let's see if there's another way for us to check. Okay, let's do VM map actually. Let's run this again. It will stop at somewhere. And then let's do VM map. That will help us to inspect the current memory layout for the program. And we see that this is the code, because first of all, it's in red. And according to the color legend, anything in red represents that this is the code, right? And also, example.out, this is the name of the address. This is the name of the binary. So it says that for this particular binary, when it's loaded into memory, it starts with this base address. And that is actually a by default address by GDB. So for us, what we want to know, what we need to do is that we need to calculate this, take this as the base address, and then plus the offset of particularly this, this program, showing this instruction shown in the program. And in order to do that, what we could do in order to do that, what we could do is that if you move your cursor over here, you will find that this function offset, right? You see that now it shows this function offset. It says this is the main function. And then it will have 7C hex. Or you can check this image-based offset. Image-based offset, it tells you that this place is with the offset of hex 914 starting from the image base. And we want to actually have this 914 add with this address. Okay, so let's use Python to calculate the value 914, right? Plus this address. Oh, I don't like that because it's not hex. Let me convert that to hex. All right, so this is the actual address. And then we can set a breakpoint again. And let me exit this. So we can have a folder window. And now let's delete the first breakpoint. Use D for short for delete. 1. And then check the breakpoint again. So you see that there's only one breakpoint. That is number 2 breakpoint, and it stops at this address. And now we can run this from over again. Okay, now it stops. It asks us for many pages in this book. I'm going to just type a random numbers over there again, right? Let's say 1, 2, 3. Okay, continue. Now it stops at the breakpoint. That's great. And then comparing to what we have from Ghidra, we know that now we're at this location. And then we want to compare these two values. We know that one of the value is the correct value. So there are 2 ways here. You could either just like check which exactly the register represent the correct value, or I can just print all, or you could do is just print them all. Let me put back here. So let's come back to this terminal. We use GDB, we look at the screen, and we found that now we're at location of here, right? This is the disassemble instruction. And we check the value of EDX, register EDX, and register EAX. So let's do P dollar EDX, that is 223, and P dollar EAX, that is 123. And remember that when we look at this, analyze this before, we know that local 8C comes from scanf. And scanf is the place that it takes an integer as an input, right? And then it's right after it asks you about how many pages. So we can infer that actually this value should be equal to the value that we just typed in, so that we know that EAX represents the value that we just typed in because it's the same value, right? It's equal to what we have just typed. And also we know that EDX is another value, which is equal to 223. All right, so now we know what we really need to put the number is 223. And then we can access this program and then run example out directly. It asks you how many pages. We just type 223 confidently, and then it will tell you that you are correct. Then here's your key. So using this way, you can kind of like reverse engineering. You can reverse engineer the actual value that is required in this program so that you will be able to get the final result, which is the key. Okay, I saw some questions, and then let me take a look. So Hunter asked, but how did 223 get into the EAX? Yes, as Matthew said, it's done at compiler time. And if you look at the code here, actually it's there. It's under this function init_i. And let's just double click that. And here is actually the value of 223. I wonder if there is highlight. Okay, I don't see the way to convert that to the decimal number, but hex df is equal to 223, and that is set up when the variable was initialized. Okay. All right. And then I saw some interesting comment, as Luke mentioned, that Ghidra was is a tool that was, long time before, well, not really that long, but like years ago, it was a secret internal tool developed by NSA, and recently NSA just publicly released it. So now we have this nice free open source tool that NSA released for us to use to analyze binary. Okay, and then more questions. Where was the local 20 variable set? Okay, let's go back to there. So local 20, this is the, right, so this is the variable, right? So this is set inside init_i. And here is the thing. So if you look at local 20, it's actually inside the stack. So it is a variable that is stored on the stack. And by the time that init_i was called, and then you see that init_i called with local 88, right? And then right after that, right after local hex 20, you see hex 88. And if you go to init8, you will see that this parameter, it goes like, it takes this parameter as input, and this is the address. And we know that is like local 88. And then what it tries to do is that it tries to access this value, access this memory, and put the value over there. So this is the way that init_i did to operate on the memory, which is those that are on stack, and assign those values there. So local 20 variable is on stack. It has a memory, and the kind of like the base of the variable was passed. The address of the base variable was passed into init_i, and init_i will operate on this memory chunk from local 88 and to the upper part, and that will touch this local 20 variable. All right. And now let's continue. Oh, and actually one more thing, Hunter, if you look at this, like right now I'm click this and you see this is the corresponding instruction. And then you found that this is RAX plus hex 68, right? And then for hex 68, if you remember local 20 and local 88, what is the offset? I mean, the difference between these two addresses is hex 68. And apparently here, RX stores the address of local 88. So that's why if you do hex plus hex 68, you'll be able to access the address of local 20 variable. All right. So now this is approach number 3. And again, for a quick recap, what we did is that we use Ghidra. We find this key instruction that we hope that it will be satisfied so that we can go to the correct outputting message instruction. And then we'll use GDB to set a breakpoint over there, check the values, understanding what exactly value that we need to put when we give this input to the program. And then we understand that, we get the value, and then we just run this program and then pass that value in. That is the way that we can go through the check correctly and get the right key. All right, and then more question from Hunter. So you will generally see an init function like that for stack variables. I mean, this not quite true, because this is just for this program. It has this init function. And if you have other program, it will have other ways to initialize a variable if they want to initialize. Otherwise, they can do something else. But if there is a statement like such, usually there should be a way. It doesn't have to be a init function. It can be just assignment, maybe within the current function that will set up the value on the stack. All right, now I'm going to close this out, and we're going to try another approach. So the last approach, which is pretty interesting, is that we are going to change the binary. So again, actually, I shouldn't close this, but like, actually, it's good. It's okay. Let's take a look at here. Like, do you remember that we're stopping at this instruction and then compare this, right? It compared this to value and then see if these two values are equal. And if it's equal, then it will go to put and it will output the actual key. So can we change the program so that the program will not output this value only when it is equal? Actually, can we change that to the way that if these two values are not equal, then it will output the actual key? Because making it not equal is actually like making your input, making your number not equal to the actual number is much easier than you find the correct answer, right? So now the question for you is, can we change the program? Change this, especially we change the binary so that the binary actually output the correct value when we don't hit the correct number, which is 223. We don't hit that. And turns out that yes, we can do it. And the way that we do it is that we find this location, we find this instruction in the binary, and then we change this instruction from JNE to JE. Like JNE means that jump if not equal, right? So we change that to jump if equal, because we want to actually output here. So if we change this to jump equal, then it will be the opposite, and it will execute this part. And now the task for us is to find this instruction. Find the instruction in our binary and edit it. Okay, now let's try to do it together. Clear this up. And then I'm going first I'm going to use opt-dump to disassemble the program and locate the instruction that I'm going to change. Now I know that this is inside main, so let's go to the main function, right? And we want to find this main plus 126, right? So it's probably somewhere else or somewhere down. You could also just have this value, have that added with 126, and you'll be able to locate the instruction. So here we can find that it is in it's a compare in the JNE, right? And then followed by that, it's put. So let's find the put instruction. There is a put instruction here. Oh wait, so here we go. This is the right address, I believe. So we want to change this instruction, right? So before that, that's a comp, and right now the right-hand side is showing the AT&T syntax, so that's why this is EAX and EDX, but here's EDX and EAX. And then it will do a jump not equal. And let's change this. And you need to search this. Like for me, I can't remember the corresponding byte for this specific instruction. However, you can just Google it. Google jump for like x86 64 JND. It is like conditional jump with for not equal. And I'm gonna just share with you the command that I found. So let me reshare. Actually, let me do this. This is faster. All right, so this is what I found for JNE jump if conditions is met, and then this the condition is not equal. Okay, and from here we know that the JNE that we were talking about is 7.5, and we find 7.5 here. Okay, so 7.5 is here. Then can we find JE? I find JE here, right? So this one and this one's kind of like this one, and it's kind of a pair. Like the operand is the same. It's all like rel 8, which is a short jump. And then the only difference is that the first byte is different. One is 74, the other is 75. So now we're gonna change 75 in our binary, change that to 74. And I'm gonna open my favorite text editor, Vim, do example.out. And then I'm gonna convert this to hex. And then try to locate the binary. All right, so let's find that location first. Let me do opt dump again. go to the main, find the instruction, find the offset as well. Right, this is 916. Let's find it out. So 916. Here we go. This is 910, offset's 910, and this is 916. Okay, so now let's change that from 75 to 74. And then now let's convert it back to the actual string, not the hex anymore. Okay. I don't know if that works. Let's try that. Okay, I'm going to type this value again. Good. So if you compare the original round one, like original one, you will not be able to get the right key if you just type a random number. But now you just type a random number and you can get the right key. Okay. And there are questions here. First of all, how did I manage to convert it to hex in Vim? I'm using this command, xxd. Okay. And let me just do this again. Out. So this, like you see my comma and a percent and then exclamation mark. That means that you want to execute a bash command. And then xxd is the command that will convert the current text in them to hex. And then you can do, again, hexxd, but then use -r, means that just revert it back. Cool. All right, so this is the fourth approach, which is a little bit more crazy, that you change the binary and then you'll be able to get the key that you want. And that's it pretty much for reverse engineering. I mean, I introduced this four approaches to you, and it's not the case. I mean, it's not that all the four approaches will be working all the time. So it's really like specific to different kinds of binary. And also it doesn't necessarily mean that these are complete approaches for you to reverse engineer. And in fact, reverse engineering is such a skillful and such a like complicated and a difficult job. But usually the more you practice, the better you will get. So if you're interested in such things, we will have assignments similar to that. And also if you're interested in more like complicated, more challenging reverse engineering, like those problems, you can also attend Pond Devils, play CTFs with us so that you will come across even cooler challenges. All right. Now let's come to the next topic about software security. So we talk about reverse engineering. We talk about how you can infer semantics from a binary, like from a compiled and executable file. Then it's not really finding the vulnerabilities yet, right? So starting from now, we're going to talk about the actual software vulnerabilities. And again, we can't cover all different kinds of software vulnerabilities in our class, unfortunately. However, I'm going to talk with you like starting from simple but very essential and then like easy to make mistakes, which will lead to severe vulnerabilities, severe like impact for a program. So I will start with something which is called like command line injection. And starting from there, I'm going to talk about stack related vulnerabilities. And if you are interested in more advanced software vulnerabilities, I highly encourage you to attend a course like CSE365, which is the software security course at ASU. You can also just like check the CSE365 videos online in my channel, or register the class in the next semester. Although it's not taught by me next semester, Fish will be there and he will give you a very cool, very interesting, and then like mind-blowing like introduction for this world of software security. Cool. All right, now let's come back to our slides. Before that, I saw questions from chat. Does Poundback work with Mac terminal or like, do I have to have Ubuntu? So you could, in theory, you could have Poundback working Mac terminal if you install GDB properly. Mac can run GDB. Yeah, so if you have GDB, but you will not be able to use GDB to run this specific binary because this binary is a Linux binary. It's not a Mac binary. And this means that you cannot run this binary on your Mac machine. So it's a goal for you to use GDB to analyze this specific ELF binary, then you have to use Linux. Otherwise, you can use GDB to analyze those like Mac file binaries. Okay, so now we're gonna start with, as I said, command line injection. So it is a type of vulnerability. It's a software vulnerability. And let's start from there first. And I have an example here. Actually, since we talk about example, let's do our cool demo here. And let me go to that place. Okay. So let's first take a look at this example. So this is a service.c file. This is the source code of the service that we're going to play with. And on the right-hand side, I'm going to run this service. Okay. So it says that welcome to our class, and you want to check your participation. You want to see if your participation has been logged into the current service. So you can like type 1, and then it will ask you for your ASU ID. For example, Tiffany B. And then it says that you already got it. So you already check yourself in. You can also type something else. For example, I do Adam. Oh, nope, I need to check first. And do Adam. And it says no such file or directory. So it means that Adam was not recorded in the participation. Okay. So now here is your task. Suppose that there is a secret file under current folder. So you see that there is a secret here. And the goal for us is to read the secret. However, if you just do cat here, or say read just to, or vim, right, to read the secret. I will tell you permission denied. Basically, you don't have the access to read the secret. And now suppose that you already know that actually if you run service and let this binary to read the secret file for you, then you will be able to read the secret. Although I will mention later on, like mechanics wise, or say like in technical speaking, why this can happen. But now let's just suppose that as long as you can let service this program to read secret, then it will be able to read secrets for you. You won't have this permission denied issue. Then what would you do? Okay. Okay. So what we could do is we can take advantage of a vulnerability called command line. And usually command line comes with this malicious, or say this vulnerable, this is not malicious, but this vulnerable state system. So system is a specific function in Linux, or say in C, that it will just like take the command as a string and then just like run this command as it is in bash. So if you put this command, for example, if the command is ls, then this will be you do ls in the current bash. And here, if you check this function, look at this function check, what it does is that it takes ID as an argument, right? And then it put the ID into the command, and then it will use system to execute this command, which is cat records with the string of ID. So if we put, say, Adam or Tiffany B as the ID, like pass that as argument into function check, then it will just do cat records Tiffany B or cat records Adam. However, if you are an attacker, then you can play with this. What you could do is that you could do like make this ID be something like 1 and then semicolon followed by another command. And then for system, it will just take this as an entire command. It will execute both cat and the second command followed by semicolon. And in fact, here, if you look at the output here, I leave this like intentionally so that you will know the exact commands that is being executed. So if we do check participation again, right? And it asks you for the ASU ID. I'm gonna just like put a random string over there. I know this person doesn't exist, but I don't care. And a semicolon, which means that I finish this current command, and then I will do cat again, secret. And let's see what's the command that will be executed. All right, so this is the actual command that is executed. This is cat record 1 followed by cat secret. And that's why you will be able to really read the secret, because according to bash, you just can read it and then you will get the secret content. And as Michael said, this is very similar to SQL injection. Yes, so it's like you secretly inject another command into this system command, this statement. And this is why it's called command injection. Basically, you just inject one more command into this statement. Okay, does that make sense to you? Cool. All right, and then quick recap. This is the example, as this is exactly what we just showed, right? And the vulnerability exists in the statement system command. And then you can change that. If the command is a proper command, then what it will do is it will execute cat records followed by the ID. However, you can kind of insert a new one by using semicolon followed by the malicious command that you want to execute. So in this way, you inject one more command and it will execute cat records Tiffany B followed by cat secret. And I just show you the demo. So now you know that in this way, you can read the secret file that you are not supposed to read. Question, why wouldn't we view the semicolon as part of the string? This is the grammar of the bash command. So basically for bash, if you have semicolon, it means that you just finish this type, like this, oops, sorry, you finish this sentence. It's like the way that you write statements for C program. All right. And then the question, then how are we going to defend about this? How are we going to avoid such vulnerability if you're going to program you're going to code a program in the future? So you want to avoid using system, and then you can replace system with more secure functions such as exec. For example, you could use execl, and actually there are a bunch of them. This is what I'm showing on the right. You see that there are, actually, guys, I forgot to share. Give me a second. New share. I want to show you the slides actually. Okay. So in terms of defense, as I said, we want to replace system with the actual exec family. And the right-hand side, they're exec with all different kinds of variations, depending on how specific the rest of argument that you want to have. So you want to have maybe not only the program, but also the arguments, but also the environment variables, etc. So for example, you could use execl, which will take the first is the path of the binary that you want to call, and then starting from the second is the argument. So this is the first argument, like arg0 is always just the binary itself, and then this is the second argument, this is the third argument, right? And then this is the environment pointer. And for more information, you can just check the manual for exec. And then come back to our example. The left-hand side is the vulnerable program. It is vulnerable to command line injection because of system command D. So what we want to do is that we want to replace system command to execl, and then we want to specify the exact numbers of argument, making sure that execl itself, it will only just execute one command at a time. So there's no way for you to insert one more command right after the cat statement. All right. Okay. And next, let me just quickly talk about why in the current setup that you can use the program to read the read the secret file, whereas if you just read the secret file directly, you will not be able to get it. And this comes to Linux file system, like Linux file permissions. So if you take a look at the current file, the directory, let me do a new share. Okay, so if we do a quick look, we use ls-l, we can get the permission here. You found that, first of all, for secret file, this is the secret file, right? So the owner and the group is root. And for users that is outside, that's not the user or out of the group, there is no read permission according to the legend showing the first place. So basically, this represents the permission of a file. And according to that, it says that if the rest 3.1 is the permission for the others, meaning that those users that are not owner and also that do not belong to the group. So in this case, it is me as Tiffany B. And let me do who am I here. You will see that the current account is Tiffany B. And also you can see that from here, right? So for me as Tiffany B, I don't have the access to secret according to the permission set up in this file. However, for service, I can run it, right? But still, if I just run it and use it to access secret, in theory, I couldn't read the secret because once you run a file, this file's current permission will be the same as the one who runs the file. However, in this file, there's a secret setup here. It is set UID 0. This means that I want to lift my current privilege from a normal user, which is like myself, Tiffany B, to the root user. And you may wonder that, that why would you want to do that? Because this can be pretty risky. Does it mean that what's necessary for you to have a file that you can allow user to lift their privilege to root or to be a higher privilege to users? And I will talk about that later. And now I'm just talking about how that works right now. So when we have this setup, we also have to enable this, like allow this binary to be lifted, the privilege to be lifted with this as setup. Like this as means that whenever I set UID, I can lift myself to a higher privileged person. Okay. And then, back to the question of why you want to do that. Why you allow a program to do a privilege escalation, right? And the answer is that sometimes in Linux operating system, you just need to do it. For example, for Sudo. So let's take a look at the permission for Sudo. Which Sudo. Okay, so see that it's very similar. It is owned by root, it is in the group of root. However, sometimes you will need to use sudo to escalate your privilege so that you could run like apt-get, or you can run, other bash command that requires a higher privilege. So having this setup is necessary, and that is why this as sign as well as set UID is still existing, although there is a potential that it can be taken advantage by attacker. But you, as a programmer, you need to be very careful if you use set UID in your program. So you want to make sure that there is no attacker like such that can take advantage set UID along with another vulnerability so that it will be able to access something that he's not allowed to. Okay, and now let's come back. Let's continue to talk about next types of vulnerability. So question, now suppose that we already fixed system statement so that we are immune to command line injection. Is the code secure now? And then turns out that it's still not, because this code is vulnerable to another vulnerability, which is called directory traversal, right? And then now let's talk about directory traversal. And then we will start with a demo with program again. All right, let's just have open a new terminal, new tab. Oh, all right, so now we have a new service. In this service, it asks you can either log in your participation or you check if your participation has been logged, and or you can exit the program. All right, so now right now let me just exit, and then we see that there's again a secret file, and if I try to read it, I'm not allowed. Then the question is, can we take advantage of this program so that we can read the secret file? And it turns out that there is a vulnerability in this file. But before I talk about that vulnerability, I will give you a few minutes for you to read this file. All right. So first of all, this file, do a print greeting, right? And if we go to print greeting, just print the welcome message. Nothing interesting over there. And then I will start to interact with humans input. And for function interaction, it will first print menu, and then it will read users input, convert users input with an integer using A to I, and then check the value of the integer. If the integer is log, then it will validate if your ESUID is legitimate, And if so, it'll just record it. Or if you want to check your participation, see if you're already logged, then it will ask you for ASU ID and then output the corresponding message, or you will exit. Okay. All right. So then now let's take a look at function check. And by the way, there is a problem with the indentation. Let me just clean this up. This will help you read it better. So there's a vulnerability in check again. So even though that we use execl so that it will not execute a second injected command, we don't check the file directory. We don't check the path. So if I am a benign person or I'm a good person, then I will put IDs such as Tiffany B or Adam. But if I am an attacker, then I could, instead of put like Tiffany B, I could put ... something, so that when it reads or when it executes this being cat, like this cat command, it will read the file that is outside of the record directory. And then we will be able to get that chance to touch the secret file. And let's try that together. Open a new tab. So let's do service. And let's say that we want to check participation. So if I'm a good person, I just type Tiffany B. It tells you that it will read this and it will tell you, oh, there's no such file directory, meaning that I was not logged in. But let's try to run this program again. Check participation. Instead of put Tiffany B, I'm gonna put ... secret. Now we'll enter this again. So the path becomes record / secret. And then it will read Tiffany's secret. And Redmond has a question. Will like ... start to get all files? That's a very good question. Let's try this. And let's see what will happen. Nope, it was said that there's no such file or directory. However, if you know the name of the file that you're going to read, then you can use this way to get the secret file. All right. Okay, and now let's go back to the slides to talk about defense. So now we talk about directory traversal. We know that the vulnerability happens, even though that we fix this system command. And again, this is because there's no check for the path that like users like send to the program, basically, which is the input to the program, right? So if ID, like if I'm a legitimate person, then I can just put my name and then it will just read this path. However, I can put a ... over there, and because there's no check for that, I will read the file that is outside of this particular location. And in order to defend that, first thing that we want to do is we want to make sure that the path is legitimate. There's no special character such as ... which will let this program to read anywhere that the users are not supposed to read. And then the other thing is that you want to put the correct permission. So for example, here you use this file and then if the program service itself is not like a root file, it's like a, it's a normal file without set2id. So that's when you do Tiffany B, like you execute the program, you are still with this current permission. And as long as your secret file is in the correct permission setup that Tiffany B was not supposed to read, then you're good to go. Or say you want to also prepare for the situation that the program service may read the secret file. And then in your secret file setup, you want to make sure that root will not be able to read your secret file, so that there's no way for any user to read that file, and then that file will also be secure and not accessible. Okay. And then for this particular case, what you could do is you want to have a path check. You want to check if the path is valid. And you could do is you want to check if this path contains like special characters such as ... or you know that this ID is supposed to be letters only or digits only. Then you want to check if path is letters only or digits only, or like something either letters or digits. All right, question. Could you also mitigate this by not storing sensitive information within the same path as the program? Well, I mean, I would say yes and no. Because if you don't store that in the same path, you can still access that if, for example, you have ... slash slash. You can still get that path, even though it's not stored within the same path. Although what you could do is you just put the secret file with a name that the attacker doesn't know. But again, the vulnerability still exists. You're not stopping the vulnerability. You just like stop the attacker to use this vulnerability to read the secret file because they don't know about the path of the secret file. However, the attacker can still take advantage of this vulnerability to read other files. All right. And now the third, which is more complicated, but also more interesting, more fun, is Stack Overflow. So far that we talked about two different kinds of vulnerabilities, command line injection and path traversal, or say directory traversal. And starting from this, we're going to touch the so-called memory corruption vulnerabilities. And in order to understand the Stack Overflow, let's first talk about Stack and understand how Stack works. Suppose that we have a program. In this program, suppose that we have function full and function bar, and you see that function bar calls function full, right? So bar calls full and then printf by. And then inside function full, it has two assignments, assigns 0 to variable x, assigns 1 to variable y, and then it prints the sum of x plus 1. All right, so question, So here, what I want to show you is that by the time that function bar calls function full, what will happen on the stack? We talked about stack last time, and we know that stack is something that will grow from the, like it will grow to the lower address, right? So now let's suppose that, 1 second. So suppose this is low address and this is high address. And we know that RBP is the base pointer. It will point to like the base of the stack. So the stack, if we add something more, it will just go that way. All right. So the first thing that we're going to do is that by the time, if we look at function full, by the time that we call function full, it will do something like this. It will have instructions such as push RBP, move RBP RSP, and sub RSP to by some value. So what does it tries to do? Can someone make a guess? All right, so let me explain this. So let's check those instructions one by one, and then you will understand what it does. So the first is push RBP. Suppose that we already have an RBP value, right? So this is the RBP value, and this is the RSP value. So what it does first is that by the time that the bar calls full, it will first save the next instruction of function full. Sorry, save that instruction into stack. And this is important because in this way, by the time that function full is finished, we will, like the computer will be able to know where is the next instruction, like where is printf is located, so that it will know that where he wants to continue to execute printf. Okay. And then by the time that we start to execute function full, the first thing is push RBP. So here's the RBP points to, and RBP will have a value. And then the first thing as like RBP, what it does is that it will save this value onto the stack, right? Because you push RBP onto the stack. So you will have saved RBP here, all right? And then the next, I will do move RBP RSP and then subtraction. And I will stop here because we are running out of time. And in the next lecture, I will talk about what will happen for the second and the third instructions. All right, that's pretty much for today. Let me stop recording.